So thank you very much, Olivier, for the introduction. And also I would like to thank the organizers for the invitation. It's really great for me being back to Toronto after quite a few years. And I would also like to thank Olivier for his talk before, because he actually set up sort of the whole picture that I will be also talking about. So as the title suggests, I will be working on the setup of Olivier, so on Schwarzschild-AdS background, but moving in a slightly orthogonal direction. So I want to study the effects of nonlinearities in the dynamics, but not for the Einstein equations, because this is a very complicated system, as Olivier showed, but rather, let's say, a scalar nonlinear equation that is sort of a toy model for the, hopefully, for the vacuum equations. Right, so let's go through a little bit of the notation that, okay, since Olivier already talked about anti-de Sitter spacetime, I don't really have to convince you or tell you too much about its properties. So the setup that we're going to talk about is, again, asymptotically anti-de Sitter spacetimes. And anti-de Sitter spacetime appeared already in the talk by Olivier. And we want to study the dynamics of nonlinear hyperbolic equations on asymptotically anti-de Sitter backgrounds. And so because anti-de Sitter spacetime has the conformal time-like boundary at infinity, this means that the correct setting to study those dynamics is given by the initial boundary value problem. So if one was to focus on the vacuum Einstein equations, like the prototypical system of hyperbolic nonlinear equations, then formulating the initial boundary value problem in a way that allows for well-posedness is non-trivial. Well-posedness was first shown by Friedrich, as already explained by Olivier, who set up the initial boundary value problem by specifying, of course, initial data on a space like hypersurface going all the way to the asymptotic boundary, and then at the boundary, imposing as boundary conditions the intrinsic conformal geometry of the boundary. Right? And if you want, within this class of boundary data considered by Friedrich, there is a unique reflecting boundary condition, and reflecting boundary conditions are the one we're going to consider in this talk, so as we can impose some confinement on the evolution and see turbulent effects appearing. So in this class of data, the unique, if you want, Dirichlet boundary condition is given by fixing the intrinsic boundary geometry to be conformally flat. So the one of anti-de Sitter spacetime, again, the one used by Olivier in his talk. Let me just say that very recently, there was, in work done by Ludovic Souet, so he identified, let's say, a slightly larger class of boundary conditions allowing for well-posedness. And within that class, he also identified a Neumann type, or more generally, a Robin type reflecting condition. So what did he prescribe? So if one were to expand the asymptotically AdS metric near the boundary, sort of at x equals 0, let's say, and using, let's say, a Pfefferman-Graham gauge, so this is the, if you want, the Taylor expansion of the metric near x equals 0 in that gauge, then if you want, prescribing the conformal class of the metric is pretty much essentially like prescribing this metric tensor here. The next order term here is just the Southern tensor of the metric G on the boundary. So it's determined by the Dirichlet data if you want. The next term is now a free piece that one can prescribe, again, in the Pfefferman-Graham theory. And prescribing this, if you want, term in the expansion, this would correspond to prescribing Neumann data for the evolution, right? So let me not go into details. Of course, again, let me just say that Souet, as with Friedrich, they proved their well-posedness results working in a gauge which is determined by flowing along conformal geodesics. One can get well-posedness using other gauges, for instance, in the wave gauge. In the latter case, what the Neumann condition really corresponds to is not very clear, but I'm not going to talk about this. Okay, so the problem that we'll be ultimately sort of interested in would be, since we have well-posedness at hand, to actually understand the long-time dynamics of the vacuum Einstein equations in this asymptotically anti-de Sitter setting. And a special case of that is, of course, the question of what happens to the log-time dynamics of small perturbations of a given asymptotically anti-de Sitter metric, for instance, anti-de Sitter spacetime or Schwarzschild-AdS, by fixing, let's say, reflecting boundary conditions at infinity. And this, as we said, this will introduce confinement to the problem. And of course, it's easy to see just by thinking a little bit about what happens, let's say, for the simplest linear toy model for the vacuum equations, namely the scalar wave equation. So for the scalar wave equation, with Dirichlet conditions at infinity, the solution is not expected, cannot actually decay as time goes to infinity, right? Because of confinement. So because of the lack of decay, one would expect that turning on, a nonlinearity to the equations would introduce probably, phenomena where, due to the nonlinear interactions of the non-decaying linear modes, one could expect, for instance, energy to be gradually transferred to higher and higher frequencies, namely turbulent phenomena appearing. And again, so here, if you want asymptotically, the asymptotically AdS picture is probably the cleanest setting in which one can study weakly turbulent phenomena associated to the Einstein equations, but this is not the only interesting situation. So already in the talk of Niels, for instance, we saw that there are other examples of spacetimes with stable trapping, where again, because of the stable trapping of the null geodesic on the spacetime, nonlinearities can still have room to develop such dynamics. Okay, so what do I mean by turbulence? So again, following Niels, I will be very generous in what I call turbulent behavior. So of course, again, here I'm sort of adopting the slightly poetic description by Zakharov, who defined turbulence as essentially the dynamics associated to systems with many, let's say, infinite degrees of freedom, which are away from thermodynamic equilibrium and develop in a chaotic fashion. Of course, this description says pretty much nothing about the dynamics. But again, the prototypical picture of turbulence that we have in mind is that associated to the evolution of fluids, right? So, and let me try to make a very poor drawing. So given a solution, let's say, of the Navier-Stokes equations in some bounded domain, and suppose that we're in the regime of a very large Reynolds number, one expects that initial perturbations lying, let's say, at scale 1, and here I'm trying to draw some vortices, as time evolves, will transfer their energy in smaller and smaller vortices, eventually leading to this cascade of energy to arbitrarily large frequencies until, let's say, friction takes over and dissipates that energy into heat. Right? So that's the prototypical picture that we have of turbulence in fluids. And let me call this turbulence of vortices, because again, for fluids in a confined setting, looking, let's say, at perturbations of a fluid at rest, it's essentially through vortices that we expect to see this transfer of energy and higher frequencies. However, in the 60s, it was sort of understood, let's say, mainly by Zakharov, but also by a lot of other people, that there is another sort of theory of turbulence that applies to a very large system of Hamiltonian PDEs describing many physical phenomena. And this sort of picture of turbulence is what people called wave turbulence or weak turbulence, and it's slightly different in nature. So in that case, let me write down a model nonlinear dispersive equation coming from a Hamiltonian. The important thing here is that I want a Hamiltonian with a non-degenerate quadratic part. Right? So think, for instance, of NLS. So the equation governing, let's say, nonlinear optics. I'm not going to care about the focusing or defocusing sign here. And let me look at the cubic interactions. So for such an equation, what happens in the evolution is the following. So of course, if one looks at the linearization of this equation, assuming that one solves this in a bounded domain, one would expect the linear solution to decompose into a number of normal modes, evolving without decaying the domain. So if one turns off the nonlinear interactions, then for small time intervals, essentially the way the solution is going to behave is that, okay, let me write here an expansion for my solution. So if that was, let's say, the expansion of my linear solution into modes, and let me introduce some eigenfunction here, then at the nonlinear level, one expects, at least for short time scale, the solution to be approximated by linear modes with an amplitude which sort of evolves slowly in time. And the equation on the, let's say, on the evolution of the amplitude really depends on the nonlinearity. And now there are sort of two regimes in which one can see a small parameter coming. You can either look at small amplitude initial data and evolve them for a long time scale, or look at large data and evolve them for a short time scale. In both settings, you can really describe your solution as being essentially a sum of time-dependent linear modes, right? So, or in other words, a sum of time-dependent linear waves, hence the name wave turbulence or weak turbulence. Now, okay, in the original works of Zakharov, because Zakharov was interested in studying in essentially developing a unifying theory for all those systems. But as an aside, he wanted weak turbulence to be sort of a toy model for the study of fluid turbulence. it was quickly understood, however, that fluid turbulence is not, even if you look at small, let's say, initial velocities, it will never be weak turbulence. This is because essentially, you see, if you look at the quasi-linear term, there is a u coming here, so you're never sort of close to a solution of a linear equation. But anyway, so this is, let's say, the theory that people usually call weak or wave turbulence, but traditionally, weak turbulence, again, falls sort of into very different regimes. And I want to specify to say this out because traditionally, let's say, in the math community, sometimes there is some confusion about which regime we're referring to. And here I'm sort of certainly referring to, one of the least, let's say, well-studied ones. So the case that was better studied, let's say, in the 60s already by Zakharov was the case of the so-called kinetic wave turbulence. And this corresponds, let's say, in the case of NLS. Of course, usually people understand, kinetic wave turbulence in some appropriate limit where one studies evolution in a box of dimensions going to infinity and with initial data of frequency 1. Now, this equation has scaling symmetry, so I can always rescale things to a box of size 1. Then kinetic wave turbulence would arise in a limit when one considers higher and higher frequency solutions, initial data, on a box of time 1, with large initial amplitude evolved for a short time scale. Now, why is this important? Because if I fix the box, let's say a torus of size 1, then at the linear level, my spectrum is fixed. It's like maybe the integers, or depending on the dimension, some integer lattice. But then, so here, let me introduce, let's say, this is the point spectrum of the linear operator. But now my solutions, essentially, you see, given the amplitude of the solution, the nonlinearity determines an effective time scale, after which essentially the nonlinearity changes substantially the behavior of the linear solution. And this means, especially the effective time scale is small, but for a time-dependent sum of linear modes, the actual frequency, if I do a Fourier transform in time, will not be localized at an exact point, but it will actually be spread out at a radius which is proportional to the inverse of the effective time. So now this picture is now what sort of separates the regime of kinetic wave turbulence and discrete wave turbulence. When the solution size is large and the effective time scale is small, essentially the spectrum becomes almost continuous. And this is the regime in which, statistically at least, if you look at, again, this high frequency limit under some statistical averaging properties, you expect to see a kinetic behavior of the solution arising. So at least in frequency space, you expect the support of the solution to move around according to a kinetic type equation. And this is what leads to, if one studies stationary solutions of these equations, this is what leads to the construction of, let's say, the Zakharov-Kolmogorov spectra. And this is actually, these spectra are what gave the name turbulence, let's say, to this behavior. At the other end, sort of this scaling argument, if we look at initial perturbations which are very small, and therefore the effective time scale is very large, the spectrum remains discrete. And this is actually the regime which, at least physically, was very poorly understood. So Nazarenko and a little bit Kartasova, both of them were students of Zakharov. They sort of said that, they say, Nazarenko actually says this explicitly in his book that, in many physical, let's say, applications, this kinetic wave turbulence, it applies very well when you study, for example, gravity waves on an ocean, or let's say unbounded domains. But if you try to reproduce the predictions of kinetic wave turbulence in a lab, you don't get them back. And this is because actually when you really confine your space in a very given, in a very finite bounded domain, you're probably in the second regime. Now, from the math sort of perspective, discrete wave turbulence was the first type of setting which was studied. So already in the questions posed by Bourgain in 2000. And for instance, so the question, for example, that Bourgain stated, okay, this is what motivated, let's say, all activity in the subject in the early 2000s, was the following. Take the cubic NLS equation, let's say on the two-dimensional torus. Can you find initial data which initially are small in HS and which grow in size to infinity as time goes to infinity? This is still an open question, but the best result we have in this direction is, of course, by Colliander, Kiel, Stafilani, Takaoka, and Tao, who proved that, again, for NLS on the torus, for any epsilon that you give me, let me write it here. So for any epsilon that you give me and any, let's say, Sobolev exponent bigger than 1, so above the conserved level, there exists initial data which, let's say, are small initially in the HS norm, but if you wait long enough, they become large enough. Of course, later on, no one knows what happens there. Right? They might decay. I mean, this is not a statement that as time goes to infinity, the HS norm grows to infinity, but nevertheless, that was, say, the first answer, let's say, in the direction of Bourgain's question. And this is really a setting of discrete wave turbulence, right? Because once you consider initial data with small size with respect to a subcritical, let's say, with respect to a norm in which the problem is subcritical, this means that for initial data which are small here, the effective time scale has to be very large, and so the spectrum remains really discrete. So, okay, so I don't want to really go into detail. So there are many works sort of have studied modifications of the original setup of Colliander, Kilstaphilani, Takaoka, and Tao. So for instance, Hani, Posader, Tsvetkov, and Vizilia studied the same equation on a background space which has one infinite direction, so r cross at T2. So this allows for some dispersion in the problem. And this slow dispersion sort of has the effect of, in the nonlinear evolution of this equation, of killing asymptotically all the non-resonant interactions, and essentially leaving only the resonant interaction sort of driving the dynamics of this system. So this means that this system can now be studied for time up to infinity, and they were able to answer Bourgain's question in this setting. So let me not say much, but I want to stress something. So far, all of the, let's say, from the math side, all of the rigorous constructions that we have in the regime of discrete wave turbulence are for dispersive equations like this. So dispersive equations with a nonlinear dispersion relation. And for those equations, one expects turbulence to happen, let's say, through energy cascades. So you expect energy to flow, from one frequency to the next in a local fashion in frequency scales. However, we will be interested in the study of wave-type equations. And as we will see, this happens in our case, but this was also, in some sense, already foreseen by Zakharov in one of his early papers. For such equations, you have, turbulence can appear without cascades. So you might have essentially phenomena where energy just teleports, in some sense, from one scale to a much bigger one without going through all the intermediate ones. So this is just as a teaser for what will follow. Anyway, so this is, let's say, the general picture of weak turbulence. And the question one might ask is, okay, so if we look now at the nonlinear equations of general relativity, namely the Einstein vacuum equations, do we see turbulent dynamics appear under confinement? And okay, the first, let's say, conjecture put forward now 20 years ago by Michalis and Gustav Holzegel is essentially a conjecture about turbulent dynamics. So the conjecture, the well-known AdS instability conjecture, is a statement that for, if you look at pure anti-de Sitter spacetime, right? So this is the simplest confining geometry you can think in that setting. And you look at small perturbations of the initial data evolved for the vacuum Einstein equations with reflecting conditions at infinity, then the conjecture says that there exists arbitrarily small perturbations, which, if you let them evolve for sufficiently long times, eventually collapse into black holes. So this is really an instability statement. But more than that, because the claim that a black hole emerges is essentially a claim that energy, which initially at the level of the initial data was small, as the initial perturbation was small, has concentrated at a small enough scale to allow for a trapped surface formation to be created according to the Hooke conjecture. Right? And again, in this setting, imposing reflecting conditions at infinity is important because we need to keep the energy confined. Otherwise, if one switches to, let's say, maximal dissipative boundary conditions, where at the linear level one has super polynomial decay, as shown by Holzegel, Luke, Szumlewicz, and Warnick, one would not expect this type of instability to occur. Okay, let me set up a little bit the notation because, again, I'm going to use I'm going to use all this notation when actually talking about the Schwarzschild-AdS problem. So that was the conjecture was put forward by Michalis and Gustav, but of course, studying the vacuum-Einstein equations, from let's say attaching that conjecture directly for the vacuum-Einstein equations is expected to be a very complicated problem. This is because if we want to construct, let's say, initial data which lead to such behavior, the easiest setting to construct such data is within some symmetry class that allows for a reduction of the problem to 1+1 dimensions. And that's easier done not for the vacuum-Einstein equations, but after adding some appropriate matter to the system. So for instance, let's look at the Einstein scalar field system in spherical symmetry. And in that case, of course, we have to study this system with reflecting boundary conditions at infinity. So we also have to specify how to prescribe boundary conditions for phi, the scalar field at infinity. Well, this can be done by prescribing either Dirichlet or Neumann data for the scalar field in terms of its expansion in powers of r near r equals infinity. So I'm not going to go into details. Let me just say that for the purpose of this talk, we'll be interested in the case of the conformally coupled value of the Klein-Gordon mass. So alpha here is going to be -1. And of course, in this case, in the conformally compactified picture, the scalar field is expected to be smooth all the way to the boundary. So this simplifies really all calculations. And well-posedness for this system, when alpha is equal to -1, already follows from the work of Friedrich. But we actually know that even for different values of the Klein-Gordon mass, we have well-posedness of this system for, let's say, reflecting, let's say, Dirichlet boundary conditions by the work of Holzigel and Skulevsky. And for a smaller range of the Klein-Gordon masses, we have well-posedness for a much wider class of boundary conditions by Holzigel and Warnick. Anyway, so the instability of AdS conjecture was first studied numerically and heuristically in spherical symmetry for this system. And the first work that addressed this conjecture was by Bizon and Rostvorovsky back in 2011. So Bizon and Rostvorovsky, first of all, studied the evolution of small initial data numerically, and they saw that indeed there exists small initial data that, after a long time lead all the way to black hole formation. But they also had a heuristic argument of why the instability occurs. What is the mechanism driving the instability? And the heuristic argument was essentially an argument of weak turbulence. Their claim was that at least at the first stage of the instability, when the solution is still relatively small, the dynamics are driven by a weakly turbulent mechanism. And so how did they set things up? So, of course, in spherical symmetry, we know that the dynamics are captured essentially by the scalar field. The metric can be reconstructed through the constraints. So let's pretend that the effective equation for the scalar field is just a nonlinear wave equation. So here, let's pretend that this is the box of under de Sitter spacetime, and on the right-hand side, I put all the nonlinear terms, and they form some sort of cubic non-local nonlinearity. And so what they said, they really, by implementing the same ansatz that I had here, so pretend that your solution can be really decomposed into normal modes of the linear equation with time-dependent amplitudes. Of course, this is possible because if you look at the basis Ek here of the spatial eigenfunction of the Laplacian, this is a complete basis of modes. So again, I will refer back to Stephen's talk later in this talk, but for now, on a function phi in this form. Now, if we want this phi to satisfy this nonlinear equation, if I plug in these ansatz, I get an infinite system of ODEs for the amplitudes. And the crucial observation here is that when you study the Einstein scalar field system, in this case with zero Klein-Gordon mass, but something similar happens also for the conformally coupled case, with Dirichlet conditions at infinity, then the spectrum, the linear spectrum, is just the integers. So in particular, it's purely resonant. And so from this system here, of course, the terms that oscillate in time fast enough, you can sort of disregard them to first order. You can expect that their contributions to the evolution sort of cancels out over larger timescales. But the resonant terms, the terms coming from the cases when this exponent here exactly cancels out, this is what will lead to secular growth, possibly secular growth of the amplitudes AK. So in this case, we have a non-trivial resonant system. And Bizon and Rostvorovsky's claim was that this resonant system is what leads to this gradual transfer of energy from low frequencies to high frequencies. Now, again, having a resonant system does not immediately imply that energy is transferred to higher frequencies. you could have a resonance system which is completely integrable. It doesn't have this energy transfer. So again, this will come up a bit later, but for now, just having a resonance system is already an indication that energy transfer might occur. Of course, a lot of people, some of them in this room, have studied this question extensively, both numerically and heuristically. I'm not going to mention all the works. Let me just say that there are many questions that are related to the ADS instability conjecture that were studied in those works, and not all of those are sort of part of this weakly turbulent picture of the initial stage of the instability, right? So for instance, okay, one can study, of course, what happens to changes in the parameters, so the Klein-Gordon mass, the boundary conditions, etc. One can study the possibility of the existence of moduli space, in the language introduced by Michalis in the previous days, of initial data for my equations. If we put the ADS initial data in the center, then the ADS instability conjecture claims the existence of initial data that collapse into black holes arbitrarily close to ADS. But do we expect the generic initial data in the neighborhood of ADS to collapse into a black hole, or do we instead expect islands of stability to exist? Again, this question has not been answered. Nevertheless, the rigorous construction of not of islands of stability, but of special periodic solutions, not of the Einstein equations, but of semi-linear toy models, has been done by Sakis Hadjikalias and Jacques Moschidis, who also proved their stability at very long time scales, at exponential time scales. So this is essentially a result from KAM theory, but I'm not going to go into details. And let me just briefly mention that when it comes to actually proving the ADS instability conjecture in some matter model, I have a rigorous proof of that result in the case of the Einstein-Masters-Vlasov system. Now, that proof goes all the way to to black hole formation. So it doesn't just deal with the first stage of the instability where you expect weak turbulence to be relevant. Nevertheless, this proof, exactly because of our lack of, let's say, general methods of proving black hole formation, essentially we only have the short pulse method of Christodoulou, a necessary ingredient of this proof is essentially dealing with the dynamics in a relatively low regularity class norm. So that's maybe not the best setting to have, let's say, a definite result of the conjecture, but nevertheless, it's one rigorous result. Anyways, but okay, this is, let's say, what one expects for perturbations of anti-de Sitter spacetime, but then one can ask the question, what happens after a black hole is formed, right? So once a black hole is formed, do we expect the spacetime to essentially settle down to one of the stationary asymptotically ADS black holes that we know of, or do we expect crazier things to happen in the exterior of the black hole? And that question, of course, is related. In fact, it's a more general question. It's related to the stability question of the stationary ADS black holes that we know. So for instance, take the Schwarzschild-AdS spacetime, which, again, in spherical symmetry, this is what one expects to form in this instability of ADS scenario. Is Schwarzschild-AdS stable or not? And that was essentially the problem introduced by Olivier in the previous hour. Of course, in spherical symmetry, the answer is yes. So this is essentially a result by Holzegel and Smolevisi. But in fact, in spherical symmetry, one expects perturbations of Schwarzschild-AdS to decay exponentially fast to ADS. And this is because in spherical symmetry, information, or if you want perturbations, so this is my Penrose diagram, can only travel radially, right? So things will fall off through the horizon pretty much infinitely. But what happens outside spherical symmetry, right? So what happens when I allow wave packets to propagate along the stable trapped null geodesics, which orbit the black hole near the boundary and never fall inside? Okay, so for this, let me do a short recap of what Olivier said. It's in much more detail and probably in a much better fashion than I will do in the previous hour. So in order to understand the nonlinear dynamics around, let's say, Schwarzschild-AdS, one better first understand very well the behavior of linear waves. Luckily for us, that was done by Gustav Holzegel and Jacques Moschidis more than a decade ago. So, okay, let's study first the linear Klein-Gordon equation of Schwarzschild-AdS in the conformally coupled case. So this is the simplest sort of type of the Klein-Gordon mass. Everything will be smooth all the way to the boundary. Now, this equation is separable, right? So, and if I separate it, essentially this equation now becomes a second order radial OD for the radial profile. And here I've drawn a picture of the potential. And what you see, the potential has a local minimum near the boundary. This is essentially another way of saying that what is hidden in this picture is essentially the statement that near the boundary I have stable trapping of null geodesics. Right? So in particular, if I look at a solution of this equation at an energy level which is below the maximum of the potential, then this solution, and okay, of course, more on that later. So if I want to study a solution of this equation with Dirichlet conditions on the boundary here, and let's say ingoing conditions towards the horizon, okay, so this will give me, let's say, a well-posed boundary value problem, then the solution I expect to be essentially localized in this classical region here, and then decay exponentially fast in this forbidden region. Right? So let me make this drawing here. And this observation, essentially because of this, we can actually construct quasi-modes. So approximate solutions of the wave equation, which sort of solve the wave equation with an exponentially small error term in the angular frequency. Right? So if I start, so how can one construct quasi-modes on Schwarzschild-AdS which with only an exponentially small error term? The simplest way, again, as implemented by Gustav and Zach, is, so here we're looking at solutions which decay exponentially fast in the frequency in the forbidden region. So I may well approximate them by putting another reflecting boundary, so a boundary where I impose Dirichlet conditions in this forbidden region here, and solve the regular Sturm-Liouville problem there, right? So this will give me a solution of some system that is not the original wave equation. It's a wave equation with some mirror, but because my solution was exponentially small in this region, if I cut it off around there, the error term that I get as a solution of the wave equation will be exponentially smaller. Right? Okay, this is the way to construct exponentially small quasi-modes for the equation. And of course, there is a general result by, let's say, Tang and Zvolsky that, let's say, in very general situations, whenever you have quasi-modes which are exponentially, let's say, which solve the wave equation with an exponentially small error term, you can always find a nearby quasi-normal mode with an imaginary part which is also exponentially small. In this case, this was established by Ganot, somehow the construction of quasi-normal modes on Schwarzschild-AdS, which, again, somehow the quasi-normal modes corresponding to this trapped, let's say, to this energy level and this trapped, the quasi-modes corresponding to this energy level and this choice of the frequency parameters will be close to the quasi-normal mode, let's say, in point-wise norms, at least near infinity. So in what follows, I will sometimes talk about quasi-normal modes or quasi-modes interchangeably. This is because they won't really affect the analysis. Okay, so the existence of quasi-modes, again, as explained by Olivier very well, essentially is an abstraction to fast decay for solutions to the wave equation, right? Because if I have a quasi-mode with an exponentially small right-hand side here, then the true solution of the wave equation with the same initial data as this quasi-mode will approximate the quasi-mode for an exponentially long time scale, right? So essentially just the existence of those quasi-modes gives me a logarithmic lower bound for any decay rate for solutions to the wave equation. And okay, in fact, Holzigel and Smolivsky actually obtained the sharp decay rates for solutions to the wave equation in Schwarzschild-AdS. So they showed that indeed, solutions to the wave equation decay logarithmically in time, and this is optimal in few of the quasi-modes. However, if I project the solution to any given spherical harmonic, the resulting expression will decay exponentially in time, albeit with a coefficient that decays exponentially fast with the frequency, right? So more on that later. This is the statement that essentially, if one wanted to obtain, for example, if one was looking at initial data, not just of Sobolev regularity, but let's say of real analytic regularity, then one would get polynomial decay rates, not logarithmic decay rates. Again, more on that in a few minutes. And of course, yes?
Can you relate the existence of the polynomial to the trapping of number?
It's exactly this, because so in some sense, the potential that appears in the wave equation to top order in the frequency parameters is the same as the potential that appears when you analyze the geodesic equation, through the separation. So this potential having a minimum up to lower order terms is the same. Again, of course, as Olivier said before me, so those results were generalized to the equations of linearized gravity around Schwarzschild-AdS. So again, I will come back to this in a moment. So now, given those results about the linear equation, so both the linear wave equation, but also the equations of linearized gravity, when addressing the question of nonlinear stability of Schwarzschild-AdS, this puts us sort of in front of a dilemma. And so the question we want to ask, is Schwarzschild-AdS nonlinearly stable or not? And okay, this is a slightly, it's less obvious what the answer should be, because for example, in anti-de Sitter spacetime, due to confinement, the solution had nowhere to escape. So one could expect that after sufficiently long time, nonlinearities could do something. But here, due to the presence of the horizon, there is some dispersion, right? So the solution decays, even though very slowly, but decays at logarithmically in time. So let me sort of try to present both arguments. So on the one hand, we have the argument against stability. So for instance, as already proposed by Gustav Holzigel and Jacques Smoulevici, in their paper on the linear wave equation, one might expect that this very slow decay of the linear quasi-normal modes, when plugging them into the nonlinear part of a nonlinear wave equation, would have sufficient time to self-interact and lead to possibly turbulent dynamics. And there has been numerical work sort of supporting this direction. So first of all, by Pau and Rossi, who looked at let's say the evolution of nonlinear of data for nonlinear equations on Schwarzschild-AdS, and for the time interval of the simulation, they didn't see any decay happening. And let me also mention the work of Benomio, Cardenas, Avendaño, Pretorius, and Sullivan, who studied not a nonlinear equation, not on asymptotically AdS spacetimes, but on other spacetimes, ultra-compact sort of stars with stable trapping. And there they also didn't see any decay happening. And in fact, okay, we'll come back to this, but they also have a conjecture about the nature of turbulence appearing there. On the other hand, again, going back more than 10 years now, Diaz, Horowitz, Marolf, and Santos, they actually try to see, to analyze the spectrum of the linear equation and try to understand if weak turbulence is expected to happen in the same way as on AdS. And so what they did is, of course, they looked now at the frequencies of the quasi-normal modes. And as before, what they want to understand is, okay, so if, suppose that you want to solve, let's say, a cubic nonlinear wave equation, you want to understand if plugging in the linear the linear modes here, again, these are of the form, let's say, so if you plug the linear expressions into the nonlinearity, will you get a combination of the time frequencies here that essentially, in a way that cancels out with another frequency in the linear part? In other words, do you have resonant interactions? And what they studied only the lowest lying quasi-normal modes. So these are the quasi-normal modes that lie, let's say, with the lowest overtone, the ones lying closest to the boundary. And they saw that the real parts of those are really non-resonant. So the first part here, this is the value of the frequency on pure AdS. And then there is a correction coming from the mass, but this constant here is non-zero. And this correction here is, it's a definite power of L. So if you were trying to force those frequencies into a resonant condition, something like a condition like that, then this term here pretty much is an abstraction to this. So, and because of this sort of, they conjectured actually stability for Schwarzschild-AdS. And their argument sort of, reinterpreted would go like this, that if at the linear level you don't have resonant interactions, again, they only studied part of the spectrum, but suppose that this is true for the whole spectrum, then by an Ecole of type stability argument from KAM theory, you would expect to not have an instability at an exponential timescale. But now, after an exponential timescale, the logarithmic decay can kick in and sort of save the system. I mean, okay, that's an interpretation sort of their argument. But Cram and Santos had recently done some numerics in higher dimensional vacuum GR, and at least for the time interval of the simulation, also didn't see an instability. So how do the two approaches combine? Okay, actually, I will state a theorem, and then I will make a conjecture that actually is consistent with both. But bear with me for 5 more minutes. Okay, so we want to understand, the nonlinear dynamics of the vacuum Einstein equations of Schwarzschild-AdS. As I said before, that's a difficult problem, right? So already from the work of Olivier, you saw that even the linearized system is, let's say, very complicated to say the least. So let's try to look for an appropriate toy model, a quasi-linear scalar wave equation to study instead of the vacuum Einstein equations. Okay, so we want a model for the vacuum equations on an asymptotically AdS spacetime, so Schwarzschild-AdS. So let me try to expand. So suppose that I have a metric G, which is a perturbation of Schwarzschild-AdS. Near infinity, Schwarzschild-AdS and AdS are sort of the same. Let me call phi their difference. So if I plug this into the vacuum equations with, let's say, in harmonic gauge, then I will get here, let's say, the linear part. Okay, let's hide the quasi-linear term somewhere here. It doesn't really matter. And here the nonlinearity will have some quadratic terms and some cubic terms. Notice this power of y here. Y equals 0 is the boundary. This is r star in the notation of Olivier. So because the AdS metric, you see, blows up near infinity, right? Infinity is conformal, it's not regular. This introduces in front of the nonlinear terms these degeneracies, right? So now the quadratic terms, of course, in such an equation, we know that these are not random terms, they have structure, right? So they satisfy the weak null condition. And what I want to do sort of some analysis of modes interacting and understanding whether there are resonant interactions. Now, by the work of Fabio and Sata, for instance, we know that for quadratic terms satisfying the strong null condition, these type of interactions can be normally transformed away into cubic terms. Now, whether such a transformation can be done for the Einstein, let's say, type of quadratic nonlinearities, that's something I don't know, but let's agree sort of to ignore the quadratic terms for the moment being when studying resonant interactions. And in the end, let's end up with this model of the Einstein vacuum equation. So this is, you see, a quasi-linear equation of cubic nonlinearity. Here, this 1 over r to the 6 is consistent with this power here. Now, the sign here can be focusing or defocusing. It doesn't matter as usual for these things. And let me just say that this nonlinearity is very similar to the one studied by Niels, already shown in his talk, right? So, albeit with the complex conjugate being at different points here. But anyway, so the importance for us of choosing exactly this type of nonlinearity is that this equation, apart from resembling, at first glance, let's say, the nonlinearity of the vacuum Einstein equations, also has a conserved H1 type energy. The nonlinearity of Niels also has the same property, but you can choose one. So let's study this equation and try to understand the stability or instability properties of this on Schwarzschild-AdS. Let me just say that, in contrast, for instance, to cubic NLS, so cubic NLS, we know on the torus, we know that solutions of this exist globally in time. So in some sense, the only pathological thing that can happen in the evolution is weak turbulence. In this case, our equation is, even though we have a conserved energy, the equation is super critical with respect to the energy. It's exactly like the vacuum Einstein equation. So for this equation, we might have finite time singularity formation. We could have all the pathological scenarios that could appear in the vacuum equations. But okay, so the theorem that we have with Christoph, which it appeared maybe a couple of months ago, is essentially the same statement as for, let's say, for NLS on the torus, but for this equation of Schwarzschild-AdS, with a small caveat. So the claim is the following. So if we study this nonlinear toy model of the vacuum equations on Schwarzschild-AdS with reflecting conditions at infinity, then for any small number epsilon that you give me and any Sobolev regularity high enough that you choose, I can find initial data which are small initially in HS, and if you wait long enough, they become large in HS. With a caveat, this is not true for all Schwarzschild-AdS spacetimes, rather for an open and dense set of Schwarzschild mass parameters. Okay, let me make a few comments before actually spending the next 10 minutes talking about the proof. So, yes? So that's a very good question. So my short answer is that I don't have a useful estimate for the time. And what do I mean by that? So secretly here, there is another parameter hiding. So the claim is that for any smallness epsilon and for any Sobolev regularity and for any large frequency that you give me, I can find such initial data at that large frequency. Now, the time scale of the interaction happening is some polynomial power of that large frequency. So polynomial depending on S, let's say the regularity. But that large frequency I can't really quantify in terms of epsilon. So for all intents and purposes, it's a soft argument in terms of the time scale. So it could be after a very long time, but that's important. Okay, let me make a few comments. Okay, first of all, our proof, okay, if I manage to say in the next 5 minutes, sort of works for complex valued scalar fields. Of course, this is not what you would like when solving the Einstein vacuum equations. But again, here we're talking about a scalar equation. You can think of, a complex valued one as being say, a two-dimensional vector. So, the Einstein equations are tensorial. This is not what would be sort of problematic in terms of generalizing. It's another part of the proof that sort of becomes tricky. Let me also say that if we fix this equation, the proof actually works on a much more general set of backgrounds which have stable trapping. Let me just say that morally speaking, if you have a stationary background with, let's say, a time-like killing vector field, or at least some way of proving energy boundedness for the wave equation using multipliers and having stable trapping, the proof for this type of nonlinear equation will go through. But the proof doesn't work if we change the exact structure of the nonlinearity. So for instance, for the cubic wave equation, the simplest possible nonlinear wave equation you can think of, our proof doesn't apply. And this has to do actually with the properties of the resonance system. So essentially, our whole proof goes through in all of those cases. But then you have to ask the question, okay, I have a resonance system of interactions. Does this resonance system lead to energy transfer or not? And this is what is not true for the cubic wave equation. It's true for, let's say, the derivative nonlinearity that we have. Okay, the other part is okay, because actually, as we will see in the proof, in the evolution of the initial data, energy transfer is not happening in a cascading way. Just there is a jump sort of among frequencies. And okay, the space, I won't comment on the space dimension here. Okay, now given this result, let me make two, let's say, natural conjectures. The first one is that given this one, it's natural to expect that Schwarzschild-AdS is unstable to HS perturbations. And in fact, the claim is that, again, as before, there exists an open and dense set of Schwarzschild-AdS mass parameters depending on the smallness of the perturbation and the Sobolev regularity, such that there exists initial data with that regularity and being epsilon small, which if you evolve long enough, they will actually create new trapped surfaces far away from the original horizon. Right? And again, this sort of is in contrast to a conjecture put forward by Gabriele, France, etc. in their paper, but okay, more on that later, because for this, of course, to be true, our method of proof wouldn't really apply, because in what we're doing, we essentially show energy transferring among modes which are L equals M modes. So they're spread out along the equator of the sphere. Of course, to see a trapped surface forming, you need your energy to be concentrated in all directions, so not having a long direction. Anyway, it's speculative anyways. But then what about all those stability results that we talked about? Well, if you look, as I mentioned before, if you look at the linear wave equation, then we said that each angular frequency actually decays exponentially fast in time, albeit with with a rate which decays also exponentially fast in their frequency. So if you look at this expression here, then for the linear wave equation, what this says is that if you initially look at initial data for which higher angular frequencies are exponentially suppressed, so you look at initial data which are small in an analytic norm, then if you sum those modes, the total solution will actually decay polynomially in time, not just logarithmically. And in fact, if you make your radius of analyticity larger and larger, you can have them decay at an arbitrary sort of polynomial decay rate. And so our conjecture is essentially the following. Now, assuming that we believe that, let's say, Kerr-AdS below the Hawking real bound is linearly stable, again, for the linear stability of Schwarzschild-AdS, Olivier talked about, the Kerr-AdS case is still open as far as I know. But anyways, so the claim is that if you look at initial perturbations which are small in an analytic norm, with a radius of analyticity determined from the geometry of the background, then actually the spacetime should be stable. So solutions should decay to some nearby Kerr-AdS family. And I claim that this sort of might explain what, let's say, Kramp and Santos saw in their numerics, because what this says is the following. Suppose that you have an initial perturbation which is of size epsilon, but very localized in frequency. This is an analytic perturbation. According to this, it should decay back to Kerr-AdS. Now, if you were trying to evolve this numerically, now, of course, I don't know anything about numerics, I'm just going to speculate here. All your cutoffs that you're going to do, they will create some high frequency corrections, but these corrections are going to be much smaller than the amplitude epsilon that you started. So if you want to measure what happens in a time scale depending by epsilon, pretty much this theorem will describe better the result than what you will see.
The numerics that they did, is in a very restricted symmetry class.
I agree, but
So we are not allowing for all possible sort of channels.
I agree. I agree.
Apart from this other issue.
I agree. And let's say here, for instance, what we do in axisymmetry, it's not clear if it works, but okay, somehow that's okay, do I have 5 more minutes?
Yeah.
Okay. So let's see, in 5 minutes, let me just give a very rough sketch of how the proof goes, pretty much hiding all the important details under a rug. So what we do is, of course, we want to construct a solution. So we want to construct initial data which are epsilon small that after a long time become 1 over epsilon in size. So we're going to look at a suitable ansatz. The ansatz we're going to consider is essentially my solution phi is going to be equal to a sum of modes with time-dependent amplitude plus an error term. Now, in this case, whatever choice of decomposition we use, either quasi-normal modes, or let's say normal modes with an inner mirror, and it's the second thing that we do, we won't have a complete system of modes, as Stephen said. So having an error term psi here is necessary. We can never have can never expect to actually decompose the solution completely. Anyway, so let's assume that we have such an ansatz. And actually, the way we choose our modes here is a bit technical. So we will split our modes here into 2 parts. So let's say 3 of them, which I will call the dominant modes. This is where the whole evolution will be, let's say, happening. And then the rest of the modes, which I will call non-resonant. And you can think of the non-resonant modes as being pretty much an error term. It's just that I want to distinguish between the 2 error terms. So the non-resonant modes will be bigger in amplitude, but I can control the revolution better through the equation. And then everything else, which is smaller in amplitude but has a messier evolution equation, I put into the error term. That's sort of morally speaking. And so how the analysis is going to go, I'm going to use some, let's say, simple ODE theory to study the evolution of the modes. I want to show that in the evolution, okay, so keep this picture in mind, the dominant modes exhibit energy transfer from the low frequency one, phi 0, to the very high frequency ones, phi plus and phi minus, while the non-resonant ones remain small. And then I need to show that in this time interval, the error term, which actually solves some quasi-linear equation, remains small. And let's say the second part is what will require a lot of nonlinear PD analysis, that sort of. Okay, here I'm just saying what I just said. So first of all, of course, understanding what happens in the evolution of the modes and what are the resonant properties of the system requires understanding the resonance structure of the linear spectrum, right? So, and what we do is that essentially, of course, we study the linear spectrum corresponding to overtones, not just the lowest ones, as let's say Diaz, Horowitz, Maroff, and Santos did, but rather at a large range of, let's say, the overtone n. And we can get an explicit, let's say, Taylor expansion where, okay, it's not important how we get those expressions here, but these are some expressions involving Hermite polynomials. They can, in principle, be computed explicitly. But for us, it's important to actually have the numerical values of the first few, let's say, terms in this expansion in n. So having such an expression for the linear modes, what we can prove is the following, that for an open, by playing with the mass parameter, this is the mass parameter of the background will come into the spectrum, we can arrange so that the frequencies of the 3 dominant modes are actually resonant. So they are resonant both in time and in the azimuthal variable. And moreover, those modes are non-resonant qualitatively non-resonant with respect to the others. So essentially, by playing with the mass parameter, we can sort of isolate 3 modes in the system to evolve resonantly. And it's important here, and this is where the linearity of the dispersion relation comes in, that I can do this by fixing pretty much an arbitrary ratio between those frequencies. So energy here will transfer from omega 0 to omega plus without going through the intermediate ones. And okay, I don't want to go into details, but if you look at the Taylor expansion of the omega frequency that we had before, this expansion allows for you to pretty much choose the mass m here that allows for these resonant relations to hold. So essentially, rewriting the resonant condition, just becomes an equality of this form. Now, the left-hand side here, you see n and lambda here are sort of discrete parameters. Lambda moves by, let's say, gaps of 1 over L. L is the frequency parameter. So the left-hand side, I can make it sort of 1 over L small, and then I can use the mass by fine-tuning the mass sort of to cancel this discrete sort of contribution. Anyways, that's how one sets up let's say the dominant system of modes. I don't want to talk about the non-resonant modes. You can pretend that these are, the non-resonant condition allows them to be controlled. And then if you look now at the dominant system of modes, these now evolve independently of pretty much of the rest of the system. So you have a 3x3 system of ODs for the dominant modes. And this is a second order in time system. For us, this was a bit hard to solve. So we essentially made a choice. So we chose to solve the system by choosing initial data, which sort of pretty much allows for a first order. This will be essentially we choose initial data so that our modes follow one of the two linear solutions of the second order OD. Right? This will be, let's say, the introducing, let's say, a slow parameter in the amplitude pretty much. So this is what forces our solution to be complex valued. We cannot have a solution which is a combination of both e to the I omega t and e to the minus I omega t. So the dominant system of modes now satisfies approximately a first order 3x3 system. And what we would like the system to do, we would like the system to transfer energy from low frequencies to high frequencies. Now that's a very definite statement about the eigenvalues of the corresponding matrix. Right? Now, what are these eigenvalues? I don't have a general answer. For this particular system, with this combination of derivatives and so on, we can prove that this linear system is essentially linearly unstable around the solution where B minus and B plus are 0 and B0 is non-zero. So energy is transferred to high frequencies. For the cubic wave equation, if you look at the analogous system, it turns out to be stable to very high order in perturbation theory. So what actually happens for a different system modeling the Einstein equations, I have no idea without doing the computations from scratch. Like that's that. Okay, so let me not talk about this. Let me just say one remark about the error term and stop there. So the analysis of the mode solution essentially tells me that the mode answers that I had for, let's call it phi tilde here, for my solution actually exhibits turbulence. But in order for this to be a meaningful statement, I have to make sure that the error term psi does not grow enough to sort of destroy that behavior in the meantime. And that's not an easy statement to make, because if you look at the equation satisfied by the error term, it pretty much satisfies a quasi-linear wave equation, but you can ignore the nonlinearity. Even the linear part of that is difficult to analyze. With the source term here essentially comes from the failure of the modes to solve exactly the original equation, right? So, and here we have two problems, sort of. The first problem comes from the linear part of the equation, which is that if you look at the coefficients of psi, the coefficients are not time dependent. These are the modes that we constructed before. And these coefficients here are large enough so that if you try to control the system, even if you put 0 on the right-hand side here, if you try to do naive energy estimates for this system in the time interval that we want, you will fail. You might get exponential growth at a much higher rate. The second problem that we have is the right-hand side here, which cannot be made arbitrarily small in frequency. And here the space dimension comes in. So if we're in even space dimensions, the right-hand side could become exponentially small in frequency. In odd space dimensions, it's actually only polynomially small with a very small, let's say, polynomial exponent. Nevertheless, the way we control this equation is, again, now we set up a system of commutator and multipliers. So we actually identify a good commutator vector field. So if you look at this equation here, this part is the linear wave equation. Any killing vector field of the background commutes well with this. If you look at these terms here with the time-dependent amplitudes, these are mostly supported along the modes propagating along the stably trapped null geodesics near the boundary. So those have an approximately helical symmetry, a symmetry with dt and dφ. So what we do is that we use the helical vector field here as a commutator and dt as a multiplier. I'm not going to go into details. This does not directly give the proof. We have to exploit more structure and more cancellations in that system, but I'm way out of time. So let me stop here, and thank you for your attention.
I was just wondering the conjecture of the stability with analytic data and with certain analyticity radius. Can we see how do we see that in this proof? How would this would presumably not work if the
it would not work exactly because essentially in this proof there is first of all a time scale determined by the size of the data and the nonlinearity in which you want there's a certain time scale in which you expect your, let's say, energy of higher order modes to grow. If your initial data are small in the analytic norm, then essentially this means that for higher frequencies, the initial data are exponentially small. This means that the time scale that you would need in order to see this growth would be exponentially large in frequency. And now for exponentially large time scales, the linear mode will actually decay in the meantime. So you see now the interplay between the analyticity radius, which tells you the exponential weight in your initial data, and the constants in the exponential smallness of the Moravec estimates, for example, that you do for each angular frequency.
So if you're above the radius, you can prove actually also then that the norm will stay small?
So let me say it like that. So if, for instance, if you wanted some simpler equation, for instance, pretend that you have some nonlinear equation which is a semi-linear one. So put here something like, and you can even put quadratic terms here, it doesn't really matter, but it doesn't matter if it's cubic or quadratic or not. Then for such an equation, what I said is true. For this equation, if you have initial data which are small in such an analytic norm, they will exist globally in time, and their L infinity norm will decay, let's say, polynomial in space. Now, if you want to work with quasi-linear equations, things become much harder. And also, let me stress here that when I talk about an analytic norm, let me go a little bit back to the statement. So this is an analytic norm only with respect to the angular frequencies. So with respect to the space directions, it's just a low regularity Sobolev norm. The reason being that in odd space dimensions, even for the linear wave equation, you would not be able to, you do not expect to be able to propagate analyticity in the radial direction. This is because the boundary is slightly singular. So anyway, so that's
thanks.
Okay, so I have maybe two questions. One is much of what you presented depends on this trapping of null infinity, right? Which in asymptotically AdS is just true. But asymptotically AdS is not the only game in town, right? So you could imagine a conformal structure to infinity, which is not AdS.
Yep.
So my question is, does one know that one must have trapping if I generalize, right, the conformal structure to infinity?
I'm not sure. So in the case when the asymptotic structure is exactly AdS,
right?
If you look in the conformal picture, pretty much you get
correct.
The case of the half sphere
cross line,
right?
and you just know that there is this null trapping, right?
No, I'm saying that essentially you get the case of half the sphere. So the AdS
correct.
boundary is just the equator,
correct.
And the equator is totally geodesic, whatever you want to say. So now you say if you're not totally geodesic on the boundary.
I'm saying more. No, I'm just saying if the conformal structure to infinity. So let's take the conformal metric. Find a conformal metric whose cotton tensor is not 0.
Okay.
Right? Then you're not AdS.
So in that case, so if you fix, so now the question is what happens if you fix a different
conformal
boundary, different boundary condition?
Does one know whether this stable trapping will persist?
So, in certain situations it will not persist because in this, if you allow yourself to look into this, let's say, class of boundary conditions, you also have dissipative boundary conditions in this.
No, with reflective. Reflective boundary conditions, but it's purely about the geometry of the conformal structure.
I would expect that, yes. I mean, it all boils down to the study of how geodesics behave under reflection. If you think of them as wave packets, whatever. If wave packets upon reflection do not lose energy, then they will remain trapped because the null geodesics have the same structure. But now it really depends on how you specify the boundary conditions, right? Because you could be dissipative.
Can I ask one more about this last thing you just said about this partial analyticity in one variable? So I assume that's for the linear wave. For linear equations, right? Because if you were to think of the non-linear equations, partial analyticity will not persist. If you're only analytic in one variable and then H5 and the remaining ones, and
so it will actually. So actually it will, but in order to see that, it comes from the fact that at the linear level you also have decay. So as time evolves, pretty much what happens is that the radius of analyticity shrinks.
Yes.
But if your solution sort of decays at some integrable rate, whatever it means, the total change in the radius of analyticity will be finite. So you can sort of close a bootstrap estimate, by.
I'm talking about like if you take Einstein equations, you take a metric, which is
Yeah.
analytic in one variable, but only H5 in the remaining ones. Surely, if you solve for a tiny amount of time, it's just H5 in all the variables.
Okay, so and here's the difference between, let's say, semi-linear and quasi-linear. For semi-linear ones, you can propagate analyticity in, let's say, some of the variables. Again, with this trick where you lose some analyticity over time. For quasi-linear equations, it depends on the structure. For example, if you have a quasi-linearity with only angular, let's say, at least one angular derivative, angular being the direction of analyticity, at least one angular, then you can still propagate. If not, then you cannot propagate. That's
Perhaps only one more question.
okay.
Maybe just a humble physicist question. Maybe we'll leave it that can apply to you as well. I'm curious about in supergravity, something we're interested in structural AdS or core AdS black holes. And one kind of thing we butt our heads against is defining something like what we call the thermal AdS phase. So something you have just, or what would just be AdS vacuum, and defining something like a black hole relative to it, or you used concept for fluid dynamics, I'll use a concept for thermodynamics, something like the free energy. You compare a black hole as stable relative to that AdS vacuum or AdS gas sometimes. Like, is that something you kind of encountered, that notion of thermodynamic stability? You have something like a free energy. You have depending on the size of something like a Schwarzschild-AdS black hole, you can address whether it is stable or not stable relative to that vacuum.
So I'm not sure what thermodynamic stability would mean. Let's say that in this case, the size of the black hole is irrelevant. So the same statement is true also for very large, let's say, very small ones, but I'm not sure what that.
The resonance system that you have constructed, it has solutions with an unbounded growth, which is the mechanism of growth, homoclinic connection, something similar.
So in some sense, no, because our resonance system is essentially 3 modes. So it's a very finite sort of dimensional vector space, and its total energy is conserved. So essentially, you live on a, let's say, finite dimensional sphere. So now your trajectories are on the sphere. So okay, we can show that our trajectories move far from the original data, but there is no notion of infinity in that space. I mean, what you're referring to could probably be the statement where you had infinitely many modes excited, and you could have your energy sort of being transferred from.
I think to NLS.
So in NLS, you have infinitely many modes, and your energy goes from one to the other. In this case, the excited modes are just 3. So there is no notion of infinity for the energy to move to. It's just that we have this parameter, which is the relative ratio of the frequencies. And so this is an arbitrary large parameter that we fix. So we say that we have arbitrary large amplification, but it doesn't go to infinity, sort of. I don't know if it makes sense.
So thanks for the talk. And
thank you. Yeah, let's